So thank you, Cersei, and good morning to everyone for coming today. In this presentation, I'm going to speak to you about a collaborative research effort funded by the Neuroscience Collaborative, which was led by the research coordinators at the Elkhorn Slough in California and Narragansett-Bay Reserve in Rhode Island, but involved a project team involving 8 NERRs, including our reserve, and a highly involved group of partners, including coastal managers, state agencies, and NGOs. Okay. This project was a direct result of a previous study involving 16 NERRs sites in 13 coastal states. It was based on an innovative approach that evaluates the ability of tidal marshes to thrive as sea levels rise according to 5 categories of resilience, which included marsh elevation, change in elevation, sediment supply, tidal range, and sea level change. The ability to understand and compare the likelihood of marshes to persist in the face of rising sea levels can form strategies to protect them. In this previous study, signs of risk were detected at all marshes, and adaptive management solutions are necessary to build tidal marsh resilience in the face of rising seas. So a little project background. Thin layer placement of dredge material, or the beneficial use of dredge material, is one viable strategy for restoring moderately resilient marshes. The majority of past studies or projects using thin layer placement are from the Southeast US or have been focused primarily on Spartina alterniflora low marsh species, and there is a need to test more regions and different plant communities. A strength of the NERRs program is the ability to test experimental approaches across geographies with consistent monitoring protocols. The goal of this study is to use this experimental approach to determine conditions where sediment addition is an effective strategy to enhance marsh resilience. So this is a conceptual diagram to show of how to enhance marsh resilience through thin layer placement of sediment. So you have a healthy marsh, which is exposed to additional inundation due to sea level rise or land subsidence. Then in the intertidal zone, high marsh plants are replaced by those typically found in the low marsh areas, and low marsh drowns and converts to mudflats. Then a layer of sediment restores the marsh vertical elevation relative to sea level, and over time, the high marsh zone expands and the low marsh plants recolonize mudflats, and the marsh thrives in place. So this map shows the locations of the 8 reserves, which took place in this coordinated TLP experiment. There were 6 sites on the East Coast, ranging from New Hampshire down to North Carolina, and 2 sites on the West Coast, which were in Central California. So my 6-word story was, sandboxes are fun, or were fun. TLP is hard, or you could say challenging. So in this experimental design, we use small 1/4 meter or 1/2 meter square frame plots for treatments. And those are pictured in the bottom left at the Wacoit Bay site. And the project team evaluated 3 different factors related to thin layer placement. The first was elevation, with plots in both the high marsh and low marsh zones. Sediment thickness, where we applied both a 7 centimeter and a 14 centimeter layer in the plots. And sediment type, whereas some sites also added a treatment which included a local dredge material or the addition of biochar to the quarry mix. And in the bottom right there, you can see Alex Demio collecting our dredge material from over at the Coast Guard site. All reserves use sediment from local quarries, which were standardized to a similar grain size. So we had similar sediment across the 8 sites. And this was a 75% sand and about a 25% silts and clays mix. This was mixed with local marsh mud to bring in some organic material and those sulfides to make the sediment a little more like real-world dredge material. And as I mentioned before, 3 reserves added a treatment looking at biochar, and 3 reserves added a treatment looking at local dredge material. So this experiment was run at each site using a block design. There are 10 blocks at each reserve, and treatments were randomized within each of the blocks. So this here shows 1 block at Chesapeake Bay, Virginia, at Goodwin Islands in the high marsh. And you could have 4 to 5 treatments per block. And here you can see a 14 centimeter quarry mix, a 14 centimeter local dredge, a control, just the frame, a control with no frame, and then a 7 centimeter quarry mix. So in total, across the 8 reserves, we had 460 total plots. And here is just a snapshot or a landscape shot at Elkhorn Slough showing their experimental design, showing 3 of their high marsh blocks in both the low and high marsh. So in each set of 4 colors in this image represents a block. Again, 3 in the high marsh and 3 in the low marsh. And then I would also like to point out these yellowish orangish squares, which were reference plots at each of the blocks. And those reference plots were situated 10 centimeters higher in each of the zones, low marsh zone and high marsh zone, and so represented the goals for our experimental plots, or ideally what we'd like to achieve with this thin layer restoration. So here's an idealized trajectory, or what a successful thin layer placement scenario might look like. For our high marsh plots, can we increase the cover of the more rare high marsh species, which are being replaced by the encroaching low marsh species? And for the low marsh plots, with increased elevation with a thin layer placement, will this decrease the amount of bare area and increase the cover in those drowning low marshes? So here are some of the monitoring protocols. Sediment was added in 2018, but plots were first monitored in 2017 to set a baseline. And then they were monitored every summer and fall up to 2020. We monitored changes in plot elevation and vegetation parameters, both cover and height, and crab burrowing, but I won't really get into crab burrowing during this talk. We also measured sediment characteristics, grain size and pore water at the end of the study. And we documented changes in the plots through the standardized photos taken at each plot during each sampling event. I also want to mention there was a greenhouse study that was also completed by Drexel University, but that will not be discussed today in the interest of time. So let's examine a little bit of the data. First, looking at changes in elevation at the Elkhorn Slough Reserve as an example. On the y-axis is plot elevation referenced to NAVD 88, and on the x-axis are showing the different monitoring timestamps from the fall of 2017, which is pre-sediment, to the fall of 2019, which is year 2 fall. We also completed a third year of sampling, but that data is still being analyzed. So data at the top of the plot is for high marsh plots, and the data at the bottom of the plot is for the low marsh plots. The dotted lines indicate target elevations for each sediment addition. So at Elkhorn Slough, they were really successful at meeting, and I apologize, for some reason those lines are not showing up, but at Elkhorn Slough, they were really successful in meeting those target elevations and maintaining them over time with the sediment additions. Most sites, and that you can see the lines in the plots now, hit their target elevations, but saw declines from that target elevation over time, either due to sediment compaction or losses from animal or storm activity. This is especially noticeable in Great Bay Reserve in the top left corner of the plot. Also note that Chesapeake, Maryland lost all their low marsh plots due to a storm activity. So those were not in the study. So this ordination plot examines the structural characteristics of sediment added to the thin layer plots compared to those of the natural marsh. Black triangles represent samples collected from ambient locations, and green squares represent samples collected from the TLP plots. Our sediment addition plots had significantly different sediment characteristics, higher percentages of sand, than those samples collected in the nearby ambient locations. This ordination plot now compares the pore water of sediment addition plots, which is the red and blue triangles, with pore water collected from 2 types of controls, the reference plots in green squares and the frame controls in purple diamonds. Here you can see that the sediment addition plots grouping together and separate from the natural plots, and this was driven by high bulk density redox and pH, higher bulk density redox and pH in the TLP plots, and lower ammonium in the sediment addition plots. Now examining some vegetation response to sediment addition. This figure shows vegetation recovery within the high marsh plots at our reserve in Chesapeake Bay, Virginia. The y-axis is percent cover, and the x-axis are those same monitoring time points over time. This plot shows data for the 7 centimeter addition in red triangles and the 14 centimeter addition, blue circles, and for local dredge material, which is the pink squares. In this case, recovery after sediment addition was fairly rapid, recovering to pre-addition levels within 6 months. Recovery was also greater in the 7 centimeter plots than in the 14 centimeter or local dredge plots. Across all reserves within the high marsh plots, regeneration rates were quite variable across sites. However, the 7-centimeter addition plots, the red triangles, recovered more rapidly than the 14-centimeter sediment addition plots, blue circles, across all sites, suggesting an early role for existing vegetation and not necessarily seedlings. By the end of 2019, or the year 2, this difference was less pronounced at most sites except for Elkhorn Slough, which you can see in the bottom left. This just shows you a photo time series showing the variability in recovery vegetation across our 7-centimeter high marsh plots at Chesapeake Bay, Virginia, from the time of pre-sediment addition in April 2018 to the fall of 2019. In the interest of time, I'm only going to discuss the trajectories for the high marsh plots. Now, moving on from trajectories to meeting marsh goals. We also had goals for the sediment additions, and this shows some data from North Carolina. On this slide, we can compare the sediment addition plots on the right side of the graph with 0 sediment additions, just the frame, 7, 14, and the biochar, dredge treatment sediment addition, to our other control plots, which were the control before sediment addition and the same unframed control after sediment addition, and our reference plots, again, which were placed 10 centimeters higher in each marsh zone. In this example, the reference level cover by low marsh species was actually not obtained by the fall of 2019, and the cover of high marsh species in subtreatments was actually lower than control plots, as seen by the dotted brown line. Oh, sorry. Across all sites, we did not observe any plots achieving cover in the reference plots by the fall of 2019, and very few achieved percent cover recorded in the control plots. The TLP plots at Elkhorn Slough did really bad, and this shows sites variability, as they have a different low marsh vegetation Salicornia than we have here on the East Coast. It was also interesting that across all sites, the percent cover in the control plots in 2019 were higher than the control plots before sediment addition. A further examination of these low marsh plots across all sites demonstrates that the sediment thickness was only significant at Wacoit Bay and Narragansett Bay, with greater recovery achieved in the 7-centimeter sediment addition plots. In addition, biochar had a strong positive effect at Narragansett Bay, while the addition of local dredge material had a strong negative effect at Chesapeake Bay, Virginia. So again, in the interest of time, I'm only showing these goals for the low marsh habitat. So some general take-home messages from this study were that plant revegetation was generally quite rapid and faster in those 7-centimeter additions. After 15 months, and we've gone out to another year now, but I'm just showing to 2019, the 7 and 14-centimeter addition plots had similar cover. We had faster recovery of vegetation at the high elevation plots. The reference level of desired plant cover was not achieved at any site, and control level was not surpassed at most places yet. We are starting to see better cover in that third year of the sampling. Didn't show this information, but there was more crab burrowing activity in the sediment addition plots. Sediment type definitely matters, and the potential for biochar amendment, although it was not observed in this study, should be further explored. And that was also quantified in the greenhouse experiment. And the effects of TLP vary across sites, so you can't really generalize from one site to another. There was not only this big field component as part of this study, but there were also a bunch of guidance documents that were produced. And these are available at the website listed below. But there was a consensus statement with 25 signatories of the project team and advisory committee, and also which summarizes this knowledge of TLP with 11 major recommendations. There was a literature review of TLP entitled Marshes. There's also a set of permitting guidelines, an overview of the sequence of navigating this process. And then there's a set of monitoring guidelines, which were those monitoring guidelines utilized in this study. Finally, last slide, or just in setting up the next slide, the next presentation, but there are some opportunities for the use of dredge material here in Virginia that are coming up. There are identifying locations for dredge material off the York Spit in Lower Chesapeake Bay. In 2019, the U.S. Army Corps of Engineers has identified the Lower York, Pahankatak, and Mob Jackson priority area for Shoreline Resiliency Project, and the Middle Peninsula is looking to establish a regional dredging program and needs to find innovative uses of dredge material. And our next speaker, again, is going to get into that a little bit more, I think. So that was it. Thank you.